Like math people are so weird. What? I don't think you can see it without the telescope. Yeah, it's happening. Big things are happening in the sky, and big things are happening here as well. We are going to look at probability set 2, which you did in groups. Let's make sure we actually did that correctly. Starting with problem 1, part A. As you may recall, we did that in class, and I asked you to do part B. Remind you of the situation because it was forever ago, I know. So, very rare deadly disease, 1 in 10,000 people have it. You're worried that you have it, so you go and you get tested at the doctor's, and the test comes back positive. So, probability of having a disease was 1 in 10,000. And you get a positive test, but the doctor tells you, well, there is some hope. I mean, the chances that the test gives you a positive result, given that so there's the idea of a false positive. That means that you, in other words, if you don't have the disease and you'll get a positive result, that happens 1% of the time. However, the chances that you'll get a positive result, given that you have the disease, if you actually have it, there's a 99% chance the test is going to pick it up. I believe those were all the information that we were given, and we wanted, in part A, the probability that, given that you actually tested positive for this disease, that you actually do have the disease. And the way that we figured that out was with Bayes' theorem. So, by Bayes, the probability of the disease given that you tested positive is going to be the probability given that you have the disease that you test positive times the probability that you have the disease over the same thing. Plus the opposite. So, what are the chances that you'll test positive given that you have the disease times the chances that you have the disease and the probability that you'll test positive given that you don't have the disease times the probability that you don't have the disease? That will be the probability of you having the disease in general. So, we actually went and we plugged these guys in. Positive given that you have the disease, there's a 99% chance of that. There was a 0.0001% chance of that. Probability that you'll test positive given that you don't have the disease, that was 1% chance, and the probability that you don't have the disease was going to be 1 minus this, which is 9999. And we calculated that, and it was 0.98%, right? Which was surprising, especially if you don't really think in terms of Bayes' theorem very often. We kind of had the thought that, oh my God, well, if you have the disease, there's a 99% chance that this thing is going to pick it up. So the chance that you have the disease and get a positive result is 99%, right? Turns out it was closer to 1%. And the reason is this number made all the difference. It's very rare to have the disease in the first place. So what you would realize is that there's a false positive 1% of the time. What this means is out of 10,000 people, 100 people are going to get a false positive result. And only one of those people, and then you're going to have the person who actually has the disease outside that. So you have 101 people who would be in your position, roughly. And so you are just one out of that 101 people, which is actually about 1% chance that you will have the disease. Okay? So we wanted to follow up on this, which brings us to B, which all groups had to do, as I recall. So I guess anyone can chime in here. How did you do B? So here you wanted to get a second opinion. You go to a different doctor who uses a different lab. Everything's all independent. They use nothing in common, let's assume. So you test positive again. with the same test, but different doctor and different lab. Now what's the probability that you have the disease? What did you guys actually do here? What did the group do? What did you guys? The probability that you have the disease is given that you test positive, and for the second time you test positive twice. What do you guys think? Yeah? Yeah, pretty much you do this, except what changes is going to be this guy. See, when a random person, and consequently that guy, because it's going to be 1 minus that. When a random person walks into the doctor's office, you kind of just assume they're just some random individual from this population. So that's their probability. However, this person already went to the doctor once. He has updated information. There's an updated chance that he might have the disease in particular. So, he or she, it's you. So basically what that's going to update is the P of D, and hence P of D complement. So the correct way to do this would be to think of 0.99 times, and in this, instead of 0.0001, you'll have 0.098. Plus 0.01 times whatever 1 minus 0.098 is. And what is that? You guys should have computed it already. What were the chances now? Yeah?
Should there be another 0 in front of the 90?
It should be 0.98%. Yes, there is another 0. .009. Here, 0.00. Yep.
I got 0.4949.
0.4939.
49.
Yeah, so now that's roughly 45.5%. Your chances of having the disease now, 49.5. Your chance of having the disease now is almost 1 in 2. Shot up a lot from 1%, which kind of makes sense. I mean, 2 positive results with a test that's 99% accurate, you kind of probably start having to face the music. What do you think is going to happen if he did another test and got positive again? What do you think is going to happen to that number? It's going to go up again. It'll keep rising until you kind of go towards that 99%. So that would be the correct answer. Basically, and this is kind of how Bayes' theorem is used, I would say, in general as a principle. I know in a class like this, I might ask you to use it once or twice, but in general, this is kind of how Bayes' theorem is used. Sometimes you're not really sure of a certain probability, you have a guess as to what something might be, but every time you take a guess and you work it out through Bayes' theorem, you get an answer, and you can plug it back into Bayes' theorem, and you can refine that answer, and you can back into, and you can run experiments over and over, and you can keep using this theorem iteratively, and you can just reuse it, and you get a better and better approximation over time, and hopefully it kind of goes towards what the actual reality is, which is what Bayes' theorem is good for. What this illustrates, and what a lot of other first-time examples would illustrate with Bayes' theorem, is that it's the kind of theorem that helps you to overcome your biases. You see, most of us would see that the probability of the positive result is 99%, and we focus on that 99%, and we think of, and that kind of blinds us to what we think the chances are. And when the actual reality is really 1%, which is a far cry from 99%, it seems surprising all of a sudden. But if you actually start to think through the problem, you'd realize, no, that 1% actually makes a lot of sense in this situation. Another kind of situation where Bayes' theorem would be useful is when you're judging whether objects or people belong to a certain group. So another very common first-time example when using Bayes' theorem, besides the smoker example and the disease example, is something like, let's say you're walking, you meet someone on campus, met them for the first time, never really seen them before, and they're very shy. Looking down at their shoes while they're talking to you, they're very uncomfortable around people and whatever. And let's say you had to guess, was this person a math major or a business major? What would you guess? Let's say for some reason those are the only two options you have. What would you guess? Now I can tell you what the average person would guess, especially the average person who hasn't taken probability. You guys are different now. The average person would guess that they met a math major as opposed to a business major. Why? Because there's this prevailing bias that business people are all like, hey man, what's going on? And they're all about networking and talking to customers and sales and yeah, you have to be an outgoing person for something like that. That's what people kind of think when they think of business person. This guy in a suit with a suitcase getting things done. In a math major, you think of some kid locked in a basement crunching numbers and this mom pushing his food under the door. Like you kind of imagine, okay, that's what a math person is. Math people are shy people. And that would be, in most cases, the wrong guess to make. Now, why is it the wrong guess to make? Well, it's because of the statistic that preceded the guess in the first place. What is the prevalence of math majors versus business majors in general? See, most people forget that, right? Compared to a business major, a math major is quite rare. It's kind of like having a rare disease, right? These math people, they got something, right? It's kind of like you're having a rare disease. It's like, for every 10 math majors, let's say, pretend you have 100 business majors, then, right, so if you find, what is the probability of actually being a math major, right? Or let's just actually look at the numbers so you can actually see. So, and this is a hypothetical example. So you meet a shy person, would you guess they're a math major or a business major? Now, most people would associate shyness with math majors. However, when you kind of look at it, let's say number of math majors, made up number, right? Let's say in the whole school, 10 math majors, whole school, okay? How many business majors would you have for each math major? Maybe 10 of them? So if you look at, so this is math majors, business majors. Let's say there are 100. And then you can say, what if 90% of the math majors are shy? And let's say there's a very relatively small percentage of business majors, right? 20% of the business majors. So we have this bias into math majors and business majors about shyness, right? Most math people is shy. So shyness is a property that you think of when you see math people. But how do these numbers actually compare when you actually represent the prevalence in the population, right? So this would mean here there are 9 shy math people. This would mean there are 20 shy business people. Plus people. Right? Which means if you meet a shy person, your sample size now has 29 people. And how many of those are actually math majors? A third of them. You're actually twice as likely to meet a shy business person as you are a math person. And so what happens is, a lot of people would make a lot of judgments based on some, it might even be a true statistical fact. It might actually be true that 90% of math people are shy versus 20%. You know, they say 80% of statistics are made up. Kind of just made that number up. But what would happen is, with these made up numbers, you can kind of see how your own bias or your own knowledge of certain statistics might cause you to make incorrect judgments. And Bayes' theorem is what saves you from this. Bayes' theorem is the one that says, no, no, no. What is the P of D in the first place? What is the thing that's in the background, in the context in which you're thinking? And Bayes' theorem is the thing that saves you from your biases. And you can constantly update it all the time and get better and better estimations for your probabilities, which is very important. Probably is going to be important. We'll do more application stuff in probability soon. But this is just an example. And there's a good book by Daniel Kahneman called Thinking Fast and Slow, which was probably a good read for most of you. So he's a psychologist and he studies heuristics, decision making, that kind of thing. And he talks about all the common logical fallacies that people make, and one of them is called the Bayesian Trap, this particular kind of thinking, when someone's bias is causing them to mistake the wrong, make the wrong guesses as the chance. And I believe in his example, he used farmers and librarians. When you meet a shy person, what are the chances that it's a farmer versus a librarian? Most people guess librarian, and that would be wrong, because there are way more farmers than librarians in the United States, right? A lot more, right? Bayes' theorem helps you with that. So it is the formula that saves us from our biases, and that's why it's important. It's a very, very useful and important thing. However, we shall move on because we have quite a few problems to get through. Hopefully we can get to the 7th one. I don't know. But you guys have to wake up, stop being so shy. I need you guys to talk to me, make sure that we're on the same page. But that was the answer to 1B and some of the significance beyond that problem. Problem 2 was the birthday problem. Which group had problem 2? Okay, what did you guys think? How did you solve this idea? Solve this problem? 23 people in a room, what is the probability that at least 2 have the same birthday? How did you guys figure that out? Is the whole group actually here?
Yeah.
What did you guys do? Do you remember?
So I think the first thing we did is we found the total combinations. I believe we did 23 choose 2 to get the total number of combinations, like possible birthdays you can match up with.
Okay. 23 choose 2. So you have 23 people. And you want to pick, I guess you want to pick 2 that have the same birthday? Is that the idea that you want to
Going
Okay.
individually.
Okay, and what did you do with that?
So I got 253 for that, and then I took 364 over 365, which is, that's the chance it's not the same, they don't have the same birthday, and I put that to the 253rd power.
253rd power.
And that got the probability that there's not the same birthday, and then I took 1 minus that to get the chance that there is the same birthday.
So you took 23 choose 2, then you multiply by 364 over 365.
And I put 364 over 365 to 23, choose 2 as the power.
That's the power. Okay. Why?
So that's the chance that any 2 people share the same birthday. Because we went like person by person. Well, that would be the chance they don't have the same birthday in that room.
Yeah, that's not good enough because one, it's based on pairs that you've chosen. Like it doesn't say anything about what about if these other 2 people might have one of the other dates. Because you've only not accounted for one specific date. You know what I mean? You pick a random pair and then you say, oh, we don't want them to be born on one random date out of the 365 dates. Here's a better way, but I do like the idea of first finding out how not to get this to happen. That is kind of the way I would try to. So what would we say? What is the probability of no 2 having the same birthday? Well, we're assuming that birthdays are independent. I think that was a hint I verbally gave. So this means if I look at, say, person 1, person 2, 3, 4, all the way up to, say, 22, 21, 20. Let's just go end it at 23. Okay. Probably here's how I would figure out that no 2 have the same birthday. Well, just think about, again, choosing from the days. Person 1, let's say he has a birthday. How many days of the year can he choose? Any one he wants, right? He can choose any of the 365 days out of the 365 days. How many days does person 2 have to choose? Well, 364. He's not allowed to pick the date that this guy picked. What about person 3? 363. He's not allowed to pick any of the previous 2 dates, right? So it's not just that 364. I don't want anyone down the line having the same birthday. Similarly, this would be 362 over 365. Dot, dot, dot. And these would all go down to, well, be 365 minus 23 plus 1. Remember, that's how we have to count that when the thing's included. So that would go down to what? What's 365 plus 23 minus 23 plus 1?
Could you go available by plus 1?
Because we're counting the first one. So remember, if you have, let's say 6 things, and you want to count down 3 factors, well, you'd start with the 6, but the 6 is the first factor. Then you move 1 down, 5, then you move 1 down, 4. You'll notice what that 4 is. That's actually 6 minus 3 plus 1, right? It's always going to be a plus 1. The plus 1 accounts for the fact that you're counting this as position 1, where most people think of it as position 0, right? They usually don't count the first position, but for us, you have to count the first position, right? That's where the P and n formula came from. Remember, it was n times n minus 1, all the way down to n minus n plus 1. It's an idea we discussed before. So it goes all the way down to that. What's 365 minus 23 plus 1? Or 366 minus 23? 340. Now, this, at least the top, you'd actually recognize that. I mean, I don't expect you to sit there in your calculator and type this out 23 times. 365 times 364 times. That's going to take forever. What is that? That's actually a number. It's not quite a factorial. It is, in fact, this guy that I just pointed out here. This would be P of 365. Choose 23. Is going to be the numerator. And the denominator is just 365 multiplied by itself 23 times. So this is 365 raised to the 23rd power. And that's going to be the probability of known to having the same birthday. Of course, what you remember here, we multiply the probabilities because we have independence. So you find the probability of this person having a different day from that, and then that, and then that, and then that. Multiply probabilities. And we'd have that number. And so now, to find the probability of all the people, at least 2 having the same birthday, this means probability at least 2 with the same birthday. That is going to be 1 minus this number. What is that? I believe it's like 0.507. 0.507? 2. Right? So slightly bigger than 50%. So it's roughly, if you round to 2 digits, it's 51% chance. You're more likely to find 2 people with the same birthday. And we actually did find a pair with the same birthday in this class. We had more than 20 people. I was kind of afraid to try that in the beginning because I've actually seen this not work. Like the whole class goes through and says it's a birthday and no one did. Just felt like you lost something even though there wasn't really anything to gain in the first place. But yeah, luckily we found one. Yeah.
We actually got the same answer
With
the other method.
I have to think about that. So you said 23. So you said 364 over 365 to the
23 choose 2. And I got 51%. Well, 1 minus
well,
that.
1 minus that?
Yeah. And I got 51%.
Yeah, I have to think about that. Because there is a combination. Remember, the combination is going to be p and n divided by n factorial. So, I don't know if that's hidden in here somewhere. Because that would be 365 factorial. Okay, what would that actually be? 365. I'd have to think about that. Speak to random people, assuming they don't have the same birthday. Yeah, I'd have to think about the sample space there. It's one of those mysteries. I have to look at your reasoning a little bit closer. I took your handout, so you explained it, right?
Yes.
That's kind of the standard way to do it, though, here. There was a part B, as I recall. How would you tweak this if we had... You were one of the 23 people and you were guessing what is the probability that someone else in the 23 has your birthday? What did you get for that?
For that, we did 364 over 365 to the 22nd.
Right?
And we subtracted that from 1.
Yes. So here it would be the same thing, except I replace the 23 with 22. Which is pretty much what you're going to do. And let's see if that got the same answer. So for part B, at least one person shares your birthday. Right, like let A be the set of them. That's enough. Okay. So it's going to be 1 minus the probability that no one shares their birthday, which means you're looking at the 22 people, because you're the 23rd person, and they're all counting down, so that's 365, choose 22 over the 365 raised to the 22. Can someone complete this?
About 52.43%.
That also what you guys got?
No.
Yeah?
Why is it 360?
Huh? Oh, you didn't, oh, you minus the 1? So it's so you subtract that from 1.47? Is that it?
Not that one,
That's what
no.
one.
We're like,
Here?
so we got between 5 and 6%, so. No.
You got between 5 and 6%? Well, that's the correct answer. So I don't know.
I
I'd have
see-
to,
I can
I'd
see
have to
that,
look closer
yeah.
at what you wrote down, because I don't even fully understand what thought process you went through to get that. But yeah, there's a 47% chance. Maybe there's a way to tweak your way to get it to work. But this would be the standard way to solve the birthday problem. So now you guys know, the birthday problem was one of those teasers, the probability teasers. Yeah.
Wait, so
So
why
now you guys know
is it 365 and not 364? Like, why is it the permutation 365?
No, you're right, so it should be 364. Because you're not counting your own birthday.
Yes.
Yeah.
So does it
Oh,
change?
maybe that's
Would
the
it still
discrepancy.
be 365 in the denominator though?
Yes. So you took your birthday out of it. So the first person of the 22 starts with 364 options. That's probably the discrepancy there.
That actually is the same number
It gives you the same number?
as that. Like I just did 1 minus that, it's 0.5017. Which is the same. Oh wait, what's the?
No, the bottom would be 364 as well, right? Because you're taking your birthday is gone out of the year, right? There are 365 days in total, but your birthday is gone. They're not allowed to choose that anymore. So everyone else now is choosing out of 364. So
Yeah,
that should
so
be
it's
364.
0.4766.
Is that what you got now? No? Okay, I still have to look up what you did. Okay, that should be right. So your birthday is taken out, so there are only 364 days that the other 22 people can choose from. The first person can choose any of the 364, the next person has to choose 363 out of the 364, the next person has to choose 362 out of the 364, and so on and so forth. But yeah, it's definitely 47 something. The details left to the reader. Let's actually continue. What is the next problem? 23 places is a lot of things to think about. Let's talk about 5 things. So what group had problem 3? So I had 5 coins on a table, 2 of them are double-headed. The rest are fair. Take a coin at random and flip. Probability that you get heads. Huh?
That was our group.
Oh, yeah, what did you guys think?
Okay, so I made a tree diagram.
Okay.
So first I did the probability of choosing each individual coin. There's 5 of them, so each is 1/5.
So you did like a 5 thing?
Yeah.
1, 2, 3, 4, 5. Okay.
And then from there,
And each of these is 1/5, 1/5, 1/5, 1/5, 1/5. Okay.
so for 3 of those coins, it's gonna be they're gonna branch off and it's gonna be 0.5 heads, 0.5 tails. And then for the other two, it's just gonna be heads, 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 heads. And those are also both 0.5, so.
Yeah, well, you could even think of it as 1, right?
Yeah,
By
you
the
can
way,
also do
yeah.
that, yeah.
So you could even do 1 arm and just probably of 1. Okay, then what?
Okay, so then, like, we saw that, like, all of those outcomes are equally probable, because,
Mm-hmm.
and so given that.
How many do we have here?
We have 10 outcomes.
10 outcomes.
They're all equally probable, and
Mhm.
7 of them give you heads, so.
And there are 1, 2, 3, 4, 5, 6, 7. 7 are heads. This means probability of heads is 7 out of 10. Yep. That one works. Nice way to do that. We can. Here's another way to do it. Using a formula. One way you can also think about this, if tree diagrams aren't your thing, or if I gave you a problem with like 20 coins on the desk and you don't want to be drawing a 20 handed tree diagram, basically what happens is we can use Bayes version 1. Of course, unofficial. Unofficial Bayes version 1. That was the probability in the following, where we can say the probability of heads is going to be the probability of heads given that you chose a fair coin times the probability of choosing a fair coin plus probability of heads given that you chose an unfair coin times the probability that you're going to choose an unfair coin. So Bayes theorem version 1 was mentioned last time. Probability of B is the same as probability of B given A times the probability of A plus B given A complement times probability of A complement. So if you chose a fair coin, what's the probability that you will get heads? Well, it's going to be a half. What's the probability that you will choose a fair coin? Well, 3 out of 5, right? Because 2 of them are unfair. Plus, what is the probability that you'll get heads given that you chose an unfair coin? Well, 1, right? That's that you have to get heads in that case. What is the probability of choosing the unfair coin? Well, 2 out of 5. So basically that gives you 3 out of 10 plus 2 out of 5, which you can create a common denominator by multiplying and dividing by 2. And that will give you 3 plus 4 out of 10, which is 7 out of 10. That's another way you could look at it. Another way still, so we can say coin 1 is, group the fair coins, coin 1, coin 2, coin 3, these are the fair guys. And the unfair can make that coin 4 and coin 5. Basically, let's call this guy, he can be heads on the first coin, tails on the first coin, heads on the second coin, tails on the second coin, heads on the third coin, tails on the third coin. We have heads on the fourth coin, but there's a fifth head here, and there's a sixth head there, and there's a seventh head there. And so another way to look at this, there'd be tons of ways, a way for everybody. That's legal. So you could have just set the sample space to be these things. H1, H2, H3, H4, H5, H6, H7, and then T1, T2, T3. You will notice, and the event that you want is just getting an H. So it's H1, H2, all the way up to H7. You would realize that the size of the sample space is 10, and the size of the event you want is 7. And so the probability of A is the size of A over the size of S. So again, 7 over 10. Tons of ways you can do that. Problem 4. But tree diagram, totally valid. That'll be fine. But there are other ways for those of you who like another way to look at it. Problem 4. The both 10 balls. We have 5 are red. 4 are blue. 1 is green. You choose 2 balls and you, at random, you replace the first selected ball before picking the second one. This is called sampling with replacement. So you replace the thing that the original choice before making the second choice. Okay, what is the probability that both are green? Okay, which group worked on this one? Yeah?
The probability of getting the first one being green is 1 out of 10, and the probability of the second is 1 out of 10, so therefore this one.
So this is the probability of the first green and second is green. How did you know to multiply them? It's independent, right? If you chose the first one as green and you throw it back in, it doesn't change any of the chances of you getting that green again. It's one choice is completely independent of the other. So you can actually multiply these. First is green times the probability that the second is green. Because you have independence. So that means we're allowed to multiply the probabilities. So probability of getting first green is 1 out of 10. Now you put it back, so there are now again 10 to choose from, and 1 of them are green. So there's a 1% chance that you will get 2 greens. D, probability both blue. What do we do here?
The same thing, but with 4
4
out
out
of
of
10.
10. Yeah, so probability that the first blue times probability that the second is blue. We can translate and into multiply when we have independence. So that's 4 out of 10 times 4 out of 10. 16% chance. C. Probability both same color.
Basically did like the probability of both being green plus the probability of both being blue plus the probability of both being green.
So this is both green, or you can get both blue, or you can get both red. And now or translates to plus because how do you know or can be plus here?
Because they're mutual.
They're mutually exclusive. How do I know they're mutually exclusive? Both situations can't have them at the same time. You can't get 2 greens and at the same time get 2 blues, because that would mean you chose 4 things. not two things as was assumed. So you either will have two greens, or in a completely separate situation, you'd have two blues, or in a completely separate situation, you'd have two reds. So because these situations do not overlap, the probability of OR is adding the different probabilities. And both green, we actually computed that already, that's 1 over 100. Both blue, we computed that already, that's 16 over 100. Computing both red is a very similar procedure. That's 5 over 10 times 5 over 10. So that's 25%. So we have 25% plus 16% plus 1%. Gives us how many percentage? Yeah?
32.
So 42% chance that you will get two of the same color. If you were to repeat this experiment 100 times, roughly 42 times, you'll actually pick the same color by doing this. By picking and then throwing it back and mixing up again and picking again. Did that 1,000 times, 10,000 times, do it 1,000,000 times. Roughly 42% of the time you'll get the same color. How do you know the probability of different color?
You did 1 minus the probability of one.
Yeah, it basically means not the same. This is probability of not the same. So you can use a complement. 1 minus the probability of the same. 1 minus 42. So you're actually more likely to not get the same color. 58% of the time you will not get the same color. So that was problem 4. Problem 5. So repeat, but without replacement. Same situation, except once you pick, you do not replace it before choosing again. Probability both green. Is that your group? Is that? Yeah.
Yeah, so we got 0% for this one. And like
Well, that
logically-
one kind of logically makes sense, right? There's one green. If you pick the green in the first situation, there's no way you can get green again. So that kind of makes sense. We can return to this and talk about how we can know this formulaically as well. But for now, just that logically makes
I don't
sense.
know, we looked at it like if you have like 10, choose 1 for like the first green,
Mhm.
and then multiply that by 9, choose 0, which would be 0. But I don't know if that's like, you know, if that'd be correct.
9 choose 0 is not 0.
It's not.
Yeah. 9 choose 0.
Oh, yeah.
That's 9 factorial divided by 0 factorial times 9 minus 0 factorial. That's actually 1. Yeah. So 9 choose 0 is not 0, it's actually 1. That's how many ways can I choose 0 things from 9 things? Well, there's one way,
Oh, yeah.
don't choose anything.
Okay.
So that wouldn't actually give you 0. But maybe after going through the others, we'll figure out how could we get to this with a formula. How did you figure out probability that both are blue?
So we did like 12 over 10 choose 2.
Okay, explain the logic here.
So I don't like have my notes with it, but I don't know, we wrote it on the paper.
Okay.
So I'm trying to remember exactly what we did. But yeah, I don't remember. Does anyone else
For
remember?
B, we had like 4 over 10 times 3 over 9. Because,
Are you in the same group?
Yeah, we're in the
okay, I
same
guess I wrote down one.
Okay.
yeah. So since there were 4 blue in the first time and there were 10 balls left,
Okay.
And then the second time you remove 1 and there's only 9 left and there's only 4. Yeah, 3 blue left. So that was 13.3%.
Right. Now, there's a little bit of nuance here because I don't want you to think that we have independence because we don't have independence here. I want you to be aware that we don't have independence. Because once you get a certain color, it does affect your probability of getting that color again, right? So it's not independent. Your choice actually affects the other choice here. So why is it that we would multiply in this particular way? Well, once you will notice that the sample space changes, so there's a different reason why we're multiplying. And why you would multiply here is, yet again, you can think of it in terms of Bayes, but I would probably prefer you to think in this situation in terms of what the conditional means. So, what you'd want to think about here is the probability of both blue. What that means is you want the probability that the first is blue and the second is blue. Now, if you cannot assume independence, what could you assume here? So we're going to get help from another formula. We do know that the probability of A given B is going to be the probability of A and B divided by the probability of B. And so, in fact, we use this when proving Bayes' formula. I can think of the AND as a product, but what you have to realize is that someone in the product is actually a condition. So the multiplication here is thought of in this way. It's the probability that the second will be blue, given that the first was blue, times the probability that the first is blue. Right? So probably that the first one is going to be blue, that's the 4 out of 10. Now, given that you got the first one to be blue, what is the probability that the second is going to be blue? Well, that's 3 out of 10. So the multiplication actually comes from the formula for conditional probability and not from independence. So this is one of those quirky problems where if you thought of it as almost like independence and you just multiply the probabilities, it will actually work out. But you have to be aware of there's a reason in the background why it's working out that way. And it's not because you automatically just mindlessly multiply probabilities whenever you see AND, because that's not always the case. But other than that, we can just go through now and just multiply probabilities in this example, just like in the previous one, except the sample size is going to change every time we make a choice. So, see, probability that both are same color. Again, probability that both, oh, and by the way, you can think of, that gives us a reason for this, because this would be, the probability of getting the green is 1 out of 10, times, what is the probability that you'll get a green given that the first one was green? 0 out of 9, right? And that's where the 0 comes from. So it's not from a combination, it's actually multiplying by that kind of probability. Both blue plus, but here we still have mutually exclusive because you can't pick more than 2 at a time. Probability that both green plus the probability that both red. So this is the probability that the first is blue times the probability that the second will be blue given that the first is blue. And this is probability that the first is green times the probability that the second will be green given that the first is green, plus the probability that the first is red times the probability that the second will be red given that the first one is red. And so that will be, this here is 12 out of 90. This here will be 12 out of 90 plus 20 out of 90, which is 32 out of 90 would be the chances here. Probability of different color in this situation is of course going to be 1 minus that. It's going to be like It's going to be that. Let's do 6. I'm sure we're going to get through 7. I probably wouldn't want to rush through 7 either because I'm gonna use it as an excuse to introduce a whole new kind of probability. It's gonna be fun. Problem 6. Which group did problem 6? Okay. So business majors are required to take these 2 math classes: Math 1108, which you're in, Math 1109, which is Calc 1 for business majors. But of course, I picked these just to kind of mess with you guys, and you're going to think, ooh, does one depend on the other? I don't want you to use that reasoning. I want you to actually use the numbers. Suppose on average 50% of students get A's in Math 1108, 10% get A's in Math 1109, 23.5% of students get an A in one or the other. What fraction get an A in both courses? Okay. How did you do this?
So I wrote a Venn diagram, and then I assigned the variables. So basically, X was, and the left ones were little 8.
X and Y?
So X and Y were inside. So like the left one was 1108, the right one was 1109, and then X was just 1108.
Okay.
So X was just 1108, and then I put Y as just 1109, and then Z as both. And then I set up a system of linear equations, so I did X plus Y equals 15, so I did it out of 100. And then X plus Z.
Okay, so you pretend 100. I mean, how are you going to get the 23.5 people?
Yeah, like it doesn't make sense, like, practically, but like it still works with the math.
Yeah,
so X plus Y equals 15, because that's I set up X plus Z would be 15, and then Z plus Y would be 10, and then
X plus Z, because 15 people will get an A. So this is A in Math 1108, this is A in Math 1109.
Yeah, and then Z plus Y would be 10. And then X plus Y would be 23.5. And then you solve for Y. And I don't have my work with me, and so I don't know what I got, but that's it.
Okay. So, I mean, when you say the students got A in one course or the other, you're not counting Z? Describe people here as getting A in one or the other?
I read one course or the other, meaning like just one course. But if you were finding Z, then you could just find X, Y, and Z and add them together. Or if you were including Z.
Yeah, well, in general, it is the inclusive order, not the exclusive one.
Okay.
So this was okay, but you'd want to include Z. So if you were going with your idea, that's probably how I would do it.
Okay.
There are nicer ways to do it, though. But this is pretty okay. This is problem 6. Here's probably one way to think about it. Let's actually call these sets something. So let X equals set of people. A in Math 1108. Y equals set of people. It can actually save us from actually solving a system of equations. So what is the probability we're given certain information. We know the probability that you're in group X as well as the probability that you're in group Y. We also know the probability that you're in group X or Y, right? This is what they told us. 15% get an A in Math 1108. So the probability that you're in group X is 0.15. Probability that you're in group Y is 0.10. The probability that you're in X or Y is 0.235. And then A asked you for what is the probability of students get A in both courses? Based on those variables, what is this asking us for? Yeah?
X and Y.
X and Y. How can I find X and Y? Yeah?
You can do px or y equals px plus py minus p and y.
Right, you can use the law of disjunction. And so, in other words, I can solve for the px and y. And that's going to be the px plus the p of y minus the probability of x or y. And so, that is going to be 0.15 plus 0.10 minus 0.235. And what's that? So that's 25 minus 23.5. That 1.5, 0.015. Is that right? Which means if you were to solve this system of equations here for z, you should get 1.5 if you assumed 100 people. So there's a 1.5% chance. What is the probability that a student will get an A in Math 1108? A student that gets an A in Math 1108 will get an A in Math 1109. What is B asking us for? Right, a student gets an A in Math 1108, which means we know they're from group X. What's probably that a student who gets an A in Math 1108 will get an A in Math 1109? So given that X has occurred, what is the probability that Y will occur? Well, we have a formula for that. So this is X and Y over the probability of X. This is going to be, we just found X and Y, 0.015 over the probability of X, it's 0.15. So that would give us what? Huh? 0.1? Okay, now the moment of truth. Are these two independent? Is getting an A in Math 1108 independent of getting an A in Math 1109? Yes?
The probability of Y is 0.1. Probability of Y given X is also 0.1.
So we know that the probability, so we know that if independent, the probability of Y given X should be equal to the probability of Y. It shouldn't matter that X actually already happened. And in fact, this is true. So this was 0.1, which is the given, and this one is 0.1 by part B. So yes, they are independent. According to these numbers, they're independent, which I just made up. They're probably actually a little bit independent because the classes don't really have anything to do with each other in real life. But it depends, I mean, I don't know, it might be different. If you have a really tough professor in 1108, which makes you a more mathematically mature person, then, yeah. So, we don't really have time to go through 7, we'll do that next time. We'll actually introduce a different kind of probability by doing that. Did any group actually get to problem 7? Like you attempted it? You guys got through it? Interesting that you're hearing. So think about what you actually did for that for next time. I'd like to see what you guys came up with.